Sure. So again, first thing that I tend to look for is algebraic things to do. I noticed right away that there's a greatest common factor of tangent. So that's probably where I would start. So that's going to give me 1 over cosecant plus 1 over cosecant squared and 1 over secant squared. And now I notice, hey, I have things that are like 1 overs. Feels like a reciprocal identity would be a good thing to use here. Get rid of the fractions. So 1 over cosecant is sine. So 1 over cosecant squared is sine squared. Similarly, 1 over secant squared is cosine. So 1 over secant squared is cosine squared. So far, so good? Okay. I take a look now, I see sine squared plus cosine squared. Woo-hoo-hoo, that I recognize. That's the first Pythagorean identity. So that says that sine squared plus cosine squared is 1. And tangent times 1 is just tangent. Not the only way you could have done that, but I think that's by far the fastest route through that. Had you tried to make common denominators right from the beginning or turn everything into sines and cosines, this can get pretty messy pretty quick. That taking the greatest common factor of tangent off as your very first step, I think makes this quite a bit quicker to kind of sort your way through. Jack, does that feel okay?
Yeah.
Okay. Not that any of those other routes that I kind of mentioned there wouldn't have been correct. I think they just get long. Amy. Sure. So I see that I know cosecant and I know that cotangent is positive. Whenever I see a problem like this and I see that something is positive or negative, what that tells me is that I'm really going to be using one of the Pythagorean identities, and that whether it's positive or negative is going to tell me whether the plus or minus should be when I square root with the Pythagorean. So I'm going to go look at the Pythagorean that involves cosecant. So that is P2, and it says 1 plus cotangent squared, I guess we're using alphas here, is equal to cosecant squared. So that's where I'll start. Negative 3 squared is 9. Subtract 1 from both sides. Cotangent squared is equal to 8. Square root both sides. Cotangent is plus or minus 2 root 2. That's the square root of 8 that I just simplified. And since I know that cotangent is positive, I can disregard the negative on the plus or minus. So cotangent just going to be root 2 over 2. Cool so far? All right. So now what I'm going to do is I'm going to go look at my identities and look for something that relates secant, cosecant, and cotangent, the 3 pieces that I have. I think the obvious one there is the second quotient identity that says cotangent alpha is equal to cosecant alpha over secant alpha. And I'm just going to rearrange this now to get the secant by itself. So I multiply both sides by secant to get it out of the denominator, and then divide both sides by cotangent. And then I can just fill in my values for secant and cotangent and rationalize my denominator. Is that okay, Amy? Sure. So again, I think on all of 1 through 6, at some point you need to use one of the Pythagoreans. I think on all of those. And that's usually a pretty good place to start if you're not sure. Who's next? Amy? Okay, so they just want the 6 identities here. So we already have cotangent. From that, immediately I can get tangent because they're just the reciprocal. So then I'm going to use the Pythagorean that involves cotangent because that's the only piece that I know. So that says 1 plus cotangent squared is equal to cosecant squared. Negative 5 over 9 squared is 25 over 81. If I add 1 to that, I get 106 over 81. If I square root both sides, that's going to be the square root of 106 over 9, plus or minus. And I remember that cosecant and sine are reciprocals. So if sine is negative, cosecant also has to be negative. Good with that. And then sine is the reciprocal of cosecant. So when I rationalize my denominator, I get negative 9 root 106 over 106. And then my last 2 I have to get are cosine and secant. If I get one, I'll automatically get the other because they're reciprocals. So let's just say, for example, I want to find cosine. Since I have cotangent and I have sine, actually, let's use tangent. That'll make it life a little bit easier, maybe. Oh, no, it won't. I want to use cotangent. So I know that cotangent is cosine over sine. So if I multiply both sides by sine, I get that cosine is sine theta times cotangent theta. And so now I can just plug them in. So I have 9 root 106 over 106 times negative 5 over 9. So the 9's reduce and the negative signs cancel. So I have 5 root 106 over 106. and then secant is the reciprocal. So when I do that, I get root 106 over 5 after I reduce. Is that okay, Amy? So really the same process as the other one, right? We're just filling all the blanks, but it's not decidedly different than the other ones. I just am recording all the extra stuff along the way. Oops. Anybody else? Okie dokie. Just double check where we left off yesterday. Okay. So today we're going to talk about section 5.3. Which is all about proving trigonometric identities. So we're going to start with just some rules to use when doing this. Only one of these rules is like a hard and fast rule. The other ones are just kind of suggestions. So the first rule is that you can work on only one side of the identity. So you can choose to work on the left side or you can choose to work on the right side, but what you can't do is work a little bit on the right and a little bit on the left and meet in the middle. That's not going to be okay. That's the only hard and fast rule that I'm going to have for you guys when doing these. The rest of these are just kind of suggestions. So the second rule is to work on the more complicated side. Not always the best idea, but most often it's going to be the best idea. So number 3 is when in doubt, rewrite everything in terms of sine and cosine. Combine fractions using a common denominator. The difference of two squares is your friend. And the last one, let's keep an eye on the prize. Always remember, keep in mind what it is you're trying to work towards, that you want to end up with the other side of the equation. Oftentimes you can get some hints about what to do by looking at where you should be going. So let's say we have tangent x plus cotangent x equals secant times cosecant x. Okay, first thing we'd want to do is decide which side we want to work on. Again, this is not a wrong answer situation, but oftentimes there's an easier side than the other. So my advice is to work on the more complicated side. Which side is the more complicated side? The addition side or the multiplication side? It's addition. Why is the addition side the more complicated side? You have two terms on the left side versus one term on the right side. Two terms is more complicated than one term. Everybody okay with that reasoning? I would work on the left side here. Going to be much, much easier to combine two things into one thing via addition than to take one thing and break it apart into two things. Do you guys kind of see that? So let's work on the addition side. Okay, anybody idea with first step what to do? Is there any algebra thing you could do? No, right? Well, it's the x is the variable. It's not like a factor. You can't do things to both sides. You can only work on one side. Mia? Okay. So Mia says, let's get them both in, with the same trig function. That seems reasonable. So she says we can write cotangent as 1 over tangent. Okay. That sounds good. Reasonable thing to do. Elvis. Well, one is in the numerator and one is in the denominator, right? So factoring it out is just going to make you could do that, but it's going to be kind of weird because you'd have 1 plus 1 over tangent squared. But that's okay if you wanted to do that. Is everybody okay with that as a step? I don't think that's a super obvious one, but you can do that. It's not wrong. And it's certainly I can see still the way through to the answer. So it's not like it's getting us further away by doing this. What do you guys think? Do we like this step or do you want to do something different? Okay. It's an okay step. Because when you're factoring, you're dividing, right? So if you divide a half by 2, it becomes 1/4. Same idea here. If you divide 1 over tangent by tangent, it's 1 over tangent squared. Mia? Nope, can't do things to both sides. Lily? Okay, I would have done that before doing this, right? If we're here, I would make a common denominator. That's what I would do here, right? I would just think about this as tangent over 1. Then I think is the most natural thing to do in this case. So the common denominator here would be tangent, right? So you can say that. Now, Lily, in fairness, I wouldn't have converted cotangent to 1 over tangent. I would have just taken them both straight to terms of sines and cosines. I think would have been the most natural thing to do first, but I think part of the, doing these is to show you guys that, like, hey, you can do it lots of different ways, and like things that you're suggesting aren't wrong. And until you've done a bunch of these, you don't really have a good notion, like any good intuition as to like, hey, what's going to be a good thing to do versus a bad thing to do versus okay, that was fine thing to do, right? Like helpful, not helpful, wrong, not wrong, but just not very helpful. Like we need some time to play around with some of these to kind of get some intuition about that. So we're here. Does anything jump out to you here? Something absolutely should. When you see things squared and plus ones, what should we be thinking? One of the Pythagorean identities, right? Specifically, we have one that says tan squared plus 1 is secant squared. Anybody with an idea now? Now, if it's me, this is where like an eye on the prize situation kind of comes in handy. I know that I have to have just a secant in my answer, right? So I would probably think about this as like 1 secant times another secant times a 1 over tangent. Because I know this piece is set. I don't want to mess with that piece anymore. You guys agree with that? Now 1 over tangent I can think of as cotangent. Now I have no more fractions. That's nice, right? Again, my final answer, what I'm shooting towards, has no fraction in it. So this is a positive, move in the right direction. Now I know somehow secant and cotangent need to cancel out to give me cosecant, right? Aiden?
You can just change cotangent to cosecant.
Yeah, I can use Q2, the second quotient identity, to rewrite that as cosecant over secant and cancel things out. And there I'm at my final answer that I was looking for. Jeez. That took a little ways to get there, though, right? Yes, Aiden?
Wouldn't it have just been quicker if you just went from sine and cosine beginning and then found the common denominator from there?
Yeah. So let's imagine that we did that. So if we just started at the beginning by rewriting everything in terms of sine and cosine, we would have been here, right? We make a common denominator. If I look at the denominators of sine and cosine, there's no common factor. So the common denominator is just going to be the product of those two, right? Just like if I had 1/2 plus 1/3. There's no common factor between those, so the common denominator is 6. Same idea here. So I'll multiply the fraction on the right by cosine, the fraction on the left by sine. So I have sine squared plus cosine squared over cosine x times sine x. Look at that numerator. Aha! Sine squared plus cosine squared is 1. And I can just think about this as the product of two little fractions here. And then using my reciprocal identities, we have secant times cosecant. And we're done. I think that was a bit more of an obvious route than the one that we took. But I wanted to do both, just to illustrate to you that you can kind of do whatever you want, as long as you're not doing like illegal algebra, and eventually you'll end up at the right spot. But it could get kind of painful, right? So the whole goal right now is to kind of develop some intuition in terms of like what are generally good things to be doing, like productive things to be doing, and what are generally not productive things to be doing, and like being able to look at the problem and kind of see what those are going to be. You know what I mean? That's the point of kind of what we're doing right now. So I don't want to just bulldoze through these and like have Mr. Kulik do them as fast as possible and not do any things that are like, you know, to do everything the easiest way, because, well, that's often not the most helpful for you guys. You know what I mean? Let's do another example. So we have cosine over 1 minus sine equals 1 plus sine over cosine. First, let's decide which side we want to work on, the left side or the right side. Is one more complicated than the other? I don't really think so. I think they're kind of both the same. They're both one fraction. If you really wanted to argue about it, I guess I would say the right-hand side maybe is slightly less complicated because the denominator is a single thing. So you could break up the fraction if you wanted to on the right. You can't do that on the left, but ugh. To me, it doesn't make any difference. They're going to be the same. So just for the sake of argument, let's pick the left side because it's kind of the natural one to pick, since there really doesn't appear to be any difference. You guys okay with that? Okay. Any ideas on what to start? Do we see anything obvious algebraic? We can do the left-hand side. Probably not. Any identity that's obvious to use on the left-hand side? Probably not. So what does this situation call for? One of the Mr. Kulik rules. So take a look at my suggestions. There's one on that list that would apply nicely to this situation, or a combination of two, perhaps. Look at Rule 5. Aiden?
Did you like multiply by 1 and form like cosine of cosine?
I wouldn't do that. What I would say is I have half of a difference of two squares right here. And I see the other half of it up here. What should I do? Well, I'm just going to multiply the top and bottom by that other half of my difference of two squares. I know it's got to end up in that numerator somehow. I'm just going to force it up there right now and see if anything good happens as a result. Is that okay with you guys? Now, keeping my eye on the prize, I'm not going to bother to distribute the cosine through that numerator. I'm just going to write it in a factored form. Because I have no cosine in the numerator of my answer that I'm trying to get to. So I know that somehow that cosine's got to reduce out of there, right? And then I multiply the denominator out. I notice that's a difference of two squares, so I can use the factoring pattern shortcut to write it as 1 minus sine squared. And I can see that you have the way to the end here, right?
Wait, were we starting for the right side or the left side?
I'm working on the left side.
Oh, I thought you were starting.
I see. I see. So I chose to work on the left. It doesn't really matter. You just do 1 minus sine to the multiply the top and bottom if you did the right side. Still want to do the same thing. Is everybody okay with how we got to this line here? Did you catch the reasoning that I used to decide to multiply by 1 plus sine x over 1 plus sine x? That's a trick that you'll use more than once. That's something you'll want to remember. Put that in your back pocket. Any ideas what to do next? Mia. Well, that's just going to get me back to where I was, right? So if I factor that, I can, and I can reduce it, but then I'm right back to where I was when I started. So you can do that. Not helpful in this case, but it's not wrong, right? You didn't do anything wrong to do that. We're just moving not in the forward direction. Aiden.
We just changed it to cosine.
So you can change it into cosine squared.
Cosine squared, that's what I meant.
Yeah. So what Aiden's observing here is that with the first Pythagorean, we have sine squared plus cosine squared is equal to 1. I can subtract sine squared from both sides to say that cosine squared is equal to 1 minus sine squared. Elvis? Oh, sorry, I thought that was a hand up. Amy. So what we did is we started with that Pythagorean, right? I subtract the sine squared from both sides. So now I have that 1 minus sine squared is equal to cosine squared. So I took my 1 minus sine squared and replaced it with cosine squared. Is that okay? Alternatively, if it feels more comfortable, you can say, okay, I know that 1 is equal to sine squared plus cosine squared. So I can replace the 1 with sine squared plus cosine squared. And when I combine, I'm left with just cosine squared. You can think about it that way also. It's accomplishing the same thing.
So then you were able to know that from one of your identities, like that is equal to 1?
Yes, that's P1. You're welcome. All right, so we're over here. What can we do here? Mia? Yeah, we can reduce, right? So we have a cosine on top, cancels one of the cosines on bottom, and that's exactly what our right-hand side is. So we're done. Oh, ooh, excuse me. Let's do another one. All right. 1 minus cosine u times 1 plus cosine u over cosine squared u is equal to tangent squared u. Which side looks more complicated? The left, right? I shouldn't say that. The left. Correct. Yeah. That's a terrible way of giving directions. Turn left here, right? What? We all agree, though, left side? Okay. What do you want to start by doing? Drake?
I might be skipping ahead, or just like, this could also be illegal algebra, as call it. But the numerator, it looks like if you're to like put it back together and explode into how do you say it, quadratic.
Yeah.
Equation.
So you want to FOIL out the numerator. Great. You might also notice that numerator is a difference of two squares, like a minus b times a plus b. Those are typically very good things. When I multiply that together, I'm going to get 1 minus cosine squared. So again, you could FOIL that out by hand, or you could use the difference of two squares factoring pattern to shortcut. That's what I use to shortcut the multiplication. But if you had to FOIL it out, it's not a big deal. It's like an extra step or whatever. You know what I mean, guys? Okay. What should we do now? Elvis?
1 minus cos squared u is sin squared.
Very good. So using the same reasoning we used over, there. Here, we can say that 1 minus cosine squared is sine squared. which is great. We've gotten rid of all the addition and subtraction now. That's excellent, since our final answer we're looking for is just tangent squared. We need to get rid of all that addition and subtraction somehow. We've done that. Mia? Perfect, yeah. Sine over cosine is tangent. So sine squared over cosine squared is tangent squared, and we're done. That might have been the easiest one so far. Part of it, though, is you're getting more comfortable with it, so it's easier to see what to do. All right. This will be the last example I have for you guys today. Those are alphas. Yeah, the half pretzel, sure. It's the fish. Yeah. All right. Which side do you want to start on? The right. Okay. What should we do first on that right-hand side? What like terms do you see? I see sine squared, sine to the 4th, sine to the 6th. I don't see any like terms. Well, I probably, if thinking about the eye on the prize, I mean, I'm going to have a cosine left over at some point. I'm just going to need 4 more of them. I don't think that distributing the cosine in is going to really help that. I mean, you could if you want to, but I would recommend against it. Is that, you see what I'm saying, Lexi? What else you guys got? Again, this I think even if you're suggesting things that we don't want to do, it's productive because you get to hear the reasoning as like why I would not or do, or why we could or could not do or would not do one of these things. That's all helpful in building intuition, right? So don't be frustrated if I'm like, I wouldn't do that, and then explain why. Those are good things. I'm happy that you're doing this. Jack. Yeah, I think that's the best place to start here. So if I look at this quantity, each one of those contain a greatest common factor of sine squared. And even better than that is I see that on the left-hand side, I need to get a sine squared multiplying somehow, and that's going to do it. So I am pretty positive this is a good idea. Is that okay with you guys? You understand my reasoning? Oops. So that's good. So I want to show you something here. What can I conclude about this piece? What does this have to become? With an eye on the prize, what is that piece going to have to turn into, Lily? It has to turn into a cosine to the 4th, right? Everybody can see that? Because we have the sine squared pulled out already. We have another cosine pulled out. That piece is somehow going to have to turn into cosine to the 4th. So we know what we're trying to get that to turn into, right? Okay. How are we going to go about doing that? Because it's not necessarily going to be a one-step. So if I look at here, I have the sine squared part. I have one cosine, and then I have a cosine to the fifth. So what I'm missing is 4 more cosines. That part that I haven't highlighted has to turn into cosine to the fourth. Is that? So just kind of doing a little eye on the prize, I can tell what it has to turn into. Getting there, well, we'll find out. Jack.
You turn 1 minus 2 sine squared, like 2 times sine squared. Turn that 1 third to 2 times cosine squared.
No. What you could do is you could like say 1 minus sine squared minus sine squared plus sine to the fourth. You could do that and then turn this chunk into a cosine squared. You could do that. You guys think that's a good idea? It's okay. It's not bad. It's not the route I would go here, but it's not a terrible idea. Okay, what else you got? Choosing this route is tough. If you look at just these two pieces, you see a greatest common factor there? Sine squared, right, is the greatest common factor. So I'm actually going to take out a negative sine squared. So that's going to turn that into 1 minus sine squared. Let me do a bracket. You guys see anything now? That was going to be the stumbling block. That was the hard part to see. Mia. So 1 minus sine squared we can turn into cosine squared? Sure. Oops. I don't know why I turned this into cosine x back up here. Obviously that's still supposed to be an alpha. Okay. This was very good now. Look at the inside. What do you see? Can't combine them.
Factor of cosine.
Yeah, there's a greatest common factor of cosine squared, though, inside the bracket, right? So let's factor that out. I'm just going to combine that into the cosine that's already out there at the end, so I don't have to write it again. Everybody's okay with that? You could write it separately. It's not a big deal. I just... What do you see now? Amy? Yeah, the 1 minus sine squared is also a cosine squared. And that's everything we needed, right? Yeep. I'll give you a second for those of you that are writing things to kind of catch up, and then we'll go back in time and show you what I would have done differently on this one. Not that what you did was wrong, but there was a little bit of a expedient way to get to your final answer than what we did, which is okay, right? What we did was fine. This worked. There's no style points for doing it faster. Those are virtual. They're like envy style points. It's like, yeah, that was a good one. But you don't get any credit for the style points. They're just for bragging rights. All right. So what I would have done differently was back all the way at this step. That piece that I've highlighted in blue looks like a quadratic to me. Right? I have a constant, something squared, and then something to the fourth. That's something in the quadratic form. You guys agree with that? So I see two things that would multiply to give me 1 and add to give me -2. That's just -1 and -1, right? So we can factor this to sine squared -1, and then sine squared -1. Then I still have the sine squared and the cosine squared at the beginning and end. Or sine squared and cosine, excuse me. Everybody okay with that? Now, this is agonizingly close to what I want, right? I want 1 minus sine squared. I have sine squared -1. What can I do to fix that? Yeah, we'll just factor out a -1. Exactly right. So that allows me to change the signs on those pieces. Actually, let's just use a bracket there. Everybody's okay with that? The 1 minus sine squareds, as we've seen a couple of times now, are cosine squareds. And when I multiply all that stuff together, negative times negative cancel out. And cosine squared, cosine to the squared, and cosine to the first become cosine to the fifth. And we'd be done there. That's a bit shorter than what you guys wanted to do, but that's okay. Again, what you did worked. So there's nothing to complain about there, right? Now, real talk here for a moment. If it was me doing this problem, I probably would have used the left-hand side and violated my own rules. Let me show you why. So what I would have noticed is that, hey, I see the greatest common, I see that this is all sines, and that's just a cosine at the end. So I know somehow this cosine to the fourth has got to turn into like all sines, right? So I would have thought, okay, well, cosine to the fourth is just cosine squared squared. And cosine squared is 1 minus sine squared. And then I can just FOIL out that piece. Oops. Oh my goodness. Cosine. Cosine, Mr. Kulik. Cosine here at the end. Goodness gracious. And then I just distribute the sines through, and I'm done. And I like that way a little bit better because notice what I didn't ever have to do. There's no factoring there, right? Like I had to FOIL, but that's, in my opinion, I'd rather do that than factor most of the time. You know what I mean? Now maybe you had to be a little bit clever to like pull that trick to say cosine to the fifth, I'm going to make cosine to the fourth times cosine. But if you're able to see that, which again, I and the prize allowed me to get the insight to do that. From there, it wasn't too bad. Because there's really kind of only one feasible thing to do at that point. There wasn't like crazy algebra things. It was just like, okay, switch these in terms of sines. Okay, got to FOIL this out now. Okay, distribute the sine through. That's what I needed. You know, there wasn't a lot of had to like be clever after the first step there. On the other one, you had to like, there's a bunch of factoring that you had to notice that sometimes it's not easy to notice, you know? All right. That's it for today. So we'll stop here. You guys should be able to do now all the way up from 47 to 62. I want to point out to you that the homework check for Sunday is only up through 30. Right? We've assigned all the way up to 62. All I'm asking for here is up to 30 this week for this Sundays. Yeah, Sergio.
Is that this Sunday?
That's this Sunday.
Okay.
Not a week from Sunday. If it was, I would make all to 62 do. But I don't think I want to do that. I'd rather have you enjoy your week off.
It'd be much more for you to check
Yeah.
in like one time.
Yeah. It feels like have your week off. You know, like if you want to do a little bit of math and try to get ahead a little bit, that's okay. But like, let's just try to get over with and enjoy your Thanksgiving week rather than Thanksgiving weekend trying to like scramble to do your math homework. You know, force you to get it done this weekend. Have a break. Okay. What do you still